This is question number 4 from part 2 of the 60th San Diego High School Honors Math Competition. This is an interesting problem with a nice solution that is not easy to find. Let S be a region in space given as a finite union of unit cubes whose corners have integer coordinates. Let A be the projection of S onto the xy plane, B the projection onto the yz plane, and C the projection onto the xz plane. Prove that the volume of region S is less than or equal to square root of the product of areas of projections A, B, and C. First of all, observe that the volume of region S is simply the number of unit cubes in three-dimensional space, and the areas of the projections are simply the number of the projected squares on planes xy, xz, and yz, which we will call A, B, and C respectively. And for simplicity, we can view the unit cubes as dots, each dot having integer coordinates x, y, and z. And accordingly, the projections, the squares in regions A, B, and C, we will view as dots with two-dimensional coordinates x and y, or y and z, or x and z. Let's partition set S of all three-dimensional dots into subsets where each subset contains all the dots from set S which have fixed xy coordinates, that is, a pair of integer indices I and j. And let's associate with each such subset the set of two-dimensional dots in region B. They are shown as red dots on the diagram, whose x-coordinates are all equal j, and analogously the set of two-dimensional dots shown with green color on the diagram in the projection region C, whose y-coordinates are fixed index I. By definition, the number of dots in each such subset is not greater than the number of green projection dots in region C and not greater than the number of red projection dots in region B. This is obvious that projection can have more dots than the given subset, but obviously it cannot be less. And let's associate with each such subset the value kij, that is the smaller of two numbers of dots in projection region B and projection region C. Since the number of dots in the selected subset is not greater than any of them, then it's not greater than their minimum. If we add all the values kij for all the subsets defined by pairs of indices I and j, then the total number n of three-dimensional dots in set S is not greater than the sum of kij. Since the value kij is defined as the minimum of two numbers ci, the number of green dots in projection region C and the number of red dots in projection region B. From this it follows that each kij is not greater than square root of bj times ci. So the number of all three-dimensional dots n of region S is not greater than the sum of square roots of bj times ci, where I and j are all pairs of indices that are used in the projection region A. Let's square both sides of the last inequality, which gives us the inequality that is shown in the box on the diagram. We have obtained the last inequality in such form so that we can apply the Cauchy-Schwarz inequality to it. In its simplest form, Cauchy-Schwarz inequality is written at the bottom of the diagram in terms of two n-dimensional vectors x and y. The equality is achieved if and only if the ratio of every two corresponding elements of two vectors, yi to xi, is the same for all indices i from 1 to n. That is, if two vectors are parallel in n-dimensional space. When we apply the Cauchy-Schwarz inequality to our current inequality, vector x consists of numbers 1, and the dimension of this vector equals the number of pairs of indices I and j that are used in the projection region A. And vector y consists of square roots of products bj times ci for all pairs of indices I and j in the projection region A. Then we rewrite the sum of products bj times ci as the product of sums of bj and ci, where I and j are all indices used in the projection region A. Now it's easy to see that the first sum of values 1 for all pairs of indices I and j is the area of projection region A, and the second sum of bj is the area of projection region B, and analogously the sum of ci is the area of the projection region C. This gives us the inequality that we're supposed to prove. This completes the proof. Notice that if all the three-dimensional dots are packed in a rectangular parallelepiped, then the total number, which is the volume of parallelepiped, equals the sum of all kij and all products bj times ci for any pair of indices I and j from the projection region A are the same, and therefore the Cauchy-Schwarz inequality reaches equality. And so in this case, n squared equals a times b times c.